Here we go. Here is a continuation of our review of how structural plans work. So the first page was general notes. This is just many different comments on things like what building code was used in the design of this project. This is a list of building codes. How much were the loads that we placed on the structural members in our design? For example, in this design, we considered a roof live load. That's a moving load other than the weight of the building itself of 20 pounds per square foot. Here's information about how much wind we designed the structure for. Looking elsewhere, here's a note about footings, which means foundations shall rest on firm natural soil. Lumber grades. The general notes really cover a wide array of information that we don't have to, we want to condense much of this information into some space that is not right here on the floor plan. We want the floor plan to show things specific to the layout of the building, like where certain structural elements are, such as beams and columns. We don't want to have to list a whole lot of information about the nature of those structural elements. We talked about how this is a shear wall call out, with 6'6" being the minimum length of shear wall that is allowed to be built. Anything less than that, and the contractor will have to call me because there's been some mistake, and I should never specify more length than is available. The type 2 refers to the edge nailing spacing, and type B refers to the hold down. So if I go over here to sheet S3.1, that's where my shear wall schedule is. This again is a bit of a review. So type 2 right there would be a type 2 shear wall, and then, oh, I see, I've indicated 4-inch spacing. So sometimes I set the shear wall type, like type 2 would have a 2-inch spacing, type 6 would have 6-inch edge nail spacing. On this instance, I did not do that, but it's actually a pretty good convention to do it that way, so that without even having to look at my shear wall schedule, if I'm looking at the plans and I see a type 2, I can just say to the contractor right off the bat, okay, that's 2-inch edge nail spacing. I didn't do that on this project. So let's look at B. That's hold down type. B, that's an HDU2, which, as we discussed, is listed in the Simpson catalog, the Simpson connector catalog, which I hope you will go online and download. I can show you right now what it would look like to do that. There we go. Okay, so I would just go to Google and type in Simpson connector catalog, wood construction connectors catalog 2021. Download complete catalog. That's it. That's all you have to do to get that catalog. And then in the catalog, you can search for HDU2 or different sizes of hold downs. Back to the plans. Okay, so that's shear wall callouts, and then the dark line, as we discussed, indicates what side of the wall, the interior or exterior, the shear wall sheathing, which could be plywood or OSB, should be installed on. Here is an image of a shear wall hold down post. Right in there. Let's turn this to red. So there's a shear wall hold down post. There is the shear wall hold down when viewed from above. And this is actually a trimmer. It's not part of the shear wall hold down post. Okay. Here is this dashed line here represents the inside edge of the thickened footing. So if we go to here, let's go back. Look at detail 17 on sheet S3.1. Boom. Right here. There is a thickened slab edge detail. Why would the slab edge have why would it be thickened? Why not just have a concrete slab that goes like that? Right? And the reason, there are a few reasons. One is that if the concrete slab just looked like this and there were no thickened slab edge, okay, then you can have this soil caving out. The soil that's right under this edge start to cave out and get hollowed out, right? due to rainwater scouring under the edge of the slab. And that's going to cause the edge of the slab to become unsupported, and that's going to cause this wall above the slab that's sitting there to become, it's going to be sitting on the edge of a slab that is unsupported. So one reason for having a thickened slab edge, here I'll make a little list. Why have a thickened slab edge? 1, prevent soil erosion. Okay? So that thickened slab edge keeps the soil that's under the slab in here, keeps it trapped under the slab so it can't escape out of the bottom. Okay? Another reason is that when concrete is poured against the ground, the top surface is often free to dry unless the contractor puts some kind of tarp or wet burlap sack on top of there. Water will evaporate from the top half. Okay. Water evaporates from the top half, but not from the bottom, or very little from the bottom. And what that does is it causes, because the soil's down there blocking the water from escaping. And so what happens then is the top half of the slab is drying and therefore shrinking. When concrete dries, it shrinks. So the top half of the slab is drying and shrinking. The bottom half of the slab remains moist and does not shrink. And then the slab curls. The slab edge will curl because the slab is shrinking on top but not on bottom. So having a thickened slab edge presents or offers a rigid edge, right? This is like a beam, okay? And a thick, deep beam is more rigid than a shallow one. So that's a beam that will make more rigid the slab edge to reduce curling, okay? So rigidifies slab edge to resist curling. Okay, and then another reason is, for a thickened slab edge, is that this slab edge penetrates down into the soil. Surface soils can be somewhat loosely compacted, which means that if you put a foundation right on top of the surface of the soil can settle. But if you found the foundation, that means bury it down somewhat deeper than the surface, it's going to tend to sit in soil that is compacted and therefore firmer, and will resist loads with less settlement than if you put a foundation right on top of the soil. So founds footing more deeply than no thickened edge. Okay, and then let's see, anything else? I think the only other reason I can think of for a thickened slab edge would be that this could be, right now we're looking at this like this wall is made of studs, okay? Like we're looking at studs. There could be a post right here. This could be a post that is supporting some big beam upstairs and imposing a huge, large amount of force onto that post, okay? That force has to get down into the soil somehow. And so what could be happening, if we look at a side view of this, is that here's the thickened slab edge, and then we have some force that comes down like this. If the thickened slab edge has depth, significant depth, and is therefore rigid, it can distribute that force out among a larger region of soil, thus reducing the amount of pressure on the soil. Remember that stress is equal to P over A. So we want to maximize A. But to maximize A, we have to be able to count on that A element being rigid enough to spread out the load over a large area. So for example, if we just had let's say a piece of paper, let's say our slab edge was that thick, okay, like a piece of paper, we would get a bunch of load right here, right under the imposed load, okay? But then the load would die off very quickly as we moved away, because the piece of paper is not rigid enough to carry load outward. So you'd get this. The load would be very localized. And so you can tell if you put a piece of wood against your chest and then push against the piece of wood, it's going to impose pressure across your entire chest. If you put a piece of paper on your chest and then push with your finger on the paper, you're going to feel that pressure on your chest right where your finger is. Okay, so we don't want this to happen. We want a thickened slab edge to spread out the load. It's out the load, thereby reducing the soil pressure. Okay, so these are the reasons why we have a thickened slab edge there. And this can also work both ways. So I'm showing here a point load coming down and then the slab edge or the foundation having to distribute it outward. We could also have clay, expansive clay soil that expands when it rains outside, and it could expand unevenly due to where the rainwater collects against the foundation. And we could have some localized area of soil swelling happening over here, and we want that to be able to we don't want to do this to the slab. We don't want that soil swelling to pick up a corner of the building. We want the building to remain rigid like this. So maybe the building gets lifted up somewhat at the corner, but there's not a huge amount of distortion of the foundation shape that will curve the foundation and then bind up a bunch of doors and windows. A thickened slab edge reduces deformation. So I'll just say reduces deformation due to soil imperfections. Think clay. You can look up expansive clay on your own and just hear YouTube discussions of expansive clay. Okay, back to the plans. So here we can see the rooms of the house. There's a closet, there's a bedroom. As we talked about in a previous session, I like to walk through the house mentally, just to have a sense of the house. There's the thickened slab edge as we discussed. This line represents the outer edge of the slab, this black line. And remember that a dashed line indicates something that is hidden from our view. Okay, so in this case, what is hiding the inside thickened slab edge from our view? Why is it hidden? 3, 2, 1. You're correct. It's hidden because it's under the edge of the slab. I mean, it's under the slab surface. Right, so when our eye looks down, I cannot see this line firsthand. It's inferred as being underneath the slab. It is there, but it's beyond my view, so it's represented with a dashed line. Here is the symbols legend, so let's just start with foundation symbols. A spread footing is just a square or rectangular footing in plan view. Plan means looking straight down on it. That is opposed to a continuous footing. So this thickened slab edge or turned down slab edge is also described as a continuous footing. It's not an isolated chunk of concrete. It actually runs around the entire perimeter of the slab. The whole slab of this building is this area. All this is concrete slab in here. And then there is a perimeter footing, a continuous footing, a thickened slab edge that runs around the edge of this whole thing. All these terms are acceptable and interchangeable. Thickened slab edge, continuous footing, turned down slab edge, perimeter footing. Here's the symbol of a wood post or a column. Post and column are used interchangeably. Post is probably just a little less formal. And that's fine because a lot of job sites are a little less formal. So here's the cross section of the post. Because when we look at a plan view, are looking at a view that is cut at knee level of the level we're standing on, looking down. That means that if there's a column, this shear wall end post is also a column. You're going to be cutting. Our view is cutting right through that column. We look at the cross section and we see its rectangular cross section. This is a 4x6. That's why it appears longer in one direction than another. And then the two lines that go like that represent continuity. They represent that this item goes for some distance longer than just a little distance. One line like this would just indicate blocking. It would mean it's just going for a very short distance, and any member, any kind of beam or joist that crosses its path, that beam or joist will prevail against this member. The fact that this has a full X or a double line means that this is going to be continuous, and it will prevail if anything smacks into it from the side. This post will continue and not be interrupted by that other thing. This is the way we specify. Just a second. Okay, this is the way we specify the post size, just a little arrow, and then the size, 4x6. It could be 4x4, 6x6, 4x8, 4x10. Okay, this is the symbols legend describing the shear wall call out that we've already looked at a few times now. I don't think there's anything new here. This is a footing call out, this hexagon with a 2.0 there. Let's see, I would hope I have a shear wall, a footing schedule around here since I left that in the symbols legend. Nope, that was dumb. Okay, there shouldn't be a footing, there should not be a footing specification here if there's no schedule. It says footing per schedule. I did not put a footing schedule on this plan, so that's an oversight, and fortunately a harmless one, because right here I've specified the foundation size of the new thickened slab edge. So this if I were drafting this right now, I'd say, oh, that's a mistake. Just delete that from the drafting. And then here's the hold down image of a shear wall hold down looking from top down, which is this. Is a bigger image of this. Same thing. Okay. Let's see. Here's the sheet number. Remember S for structural. An architectural sheet will have A 2.0, a plumbing sheet P 2.0, mechanical engineer like HVAC would have M 2.0, electrical engineer E 2.0. Let's talk a little bit more about page numbering. So the first thing you'll notice, we've discussed what S is. Let's look at the 1, okay? This means general notes sheets. So we have S 1.0. So that means general note, it's structural general notes sheet 0, okay? The next sheet is a general notes sheet, whoops. Assume there's text on this sheet, okay? So we would have structural, and then 1 means general notes, 0. So that's the first, or the 0th sheet, okay? We get to the next sheet, and this should say 1. So this sheet would be S 1.1, like that, okay? So as many, then the next general notes sheet would be, it would be, if there were another one, S 1.2.2. Like that, and then S 1.3 and so on, okay? Like that. So we would have all those sheets. I wouldn't write them all right there in the same spot, but that would be the order of the general note sheets. Then when we're done with our general note sheets, we would go into the plan views, right? So that's S2 point, right? S2.0, S2.1, okay? And then if we had details, which every job should, then the details would be the 3.0 sheets. 3.0, and then the next sheet, see these are all details. Then the next sheet of details is 3.1, right? And then 3.2, 3.3, however many sheets of details I need. So if a contractor says to me, where's your foundation plan? I'd say it's going to be S2.0. I just know already that'll be S2.0. It'll be the first of the plan sheets. If the contractor says, what sheet are your general notes? I'd say that's the S1 series, S1.0, S1.1. If you said, oh, where are the detail sheets? I'd say that's the S3.0, S3.1, S3 series sheets. So that's the foundation symbols legend. Let's see, what else on the foundation haven't we talked about? Cross hatching of a wall. That usually means that's a new wall that's being installed. Let's look at, here's the roof framing plan. So this image is as if you're standing on the roof and an image is cut through your knee level looking down on the roof. So this indicates what? So this is the trusses, existing trusses. This indicates their extent, right? Where do they start? Where do they stop? Or where do they start? Where do they stop? They go from here to here, right? Those are the trusses, and then that's a single truss, right? This is saying each truss goes this far. And then the extent arrows here are telling you over what range of the building is that true, okay? So, again, this line in here with the angled edge, the half arrow edge, indicates the extent of a single truss, and these extent arrows indicate where those single trusses exist. They exist along the building. Probably almost always every 2 feet on center does that type of truss exist. In this small area, we have other framing. In this case, it's rafters running this way, and they exist over an extent defined by this region, by these arrows, right? And then we have more rafters here at 2 feet on center. Almost always the roof framing is spaced 2 feet apart, and these arrows indicate the extent over which those rafters exist. Notice that the rafters here are traveling perpendicular to the ridge. This is the ridge, roof ridge. All right, so when you're looking at a roof, the roof looks like this, right? And there's the house. That is the ridge, right? That peak is the ridge. And the rafters almost always run perpendicular to the ridge. So the rafters are going to be like this. It's bad drawing, but the rafters will go like that. So if you are drafting roof framing and you're wondering which way to draw the rafters going, you just look at the ridge right there, and then you know the rafters are going to go perpendicular to the ridge. Okay. Here's the ridge in this image. So therefore the trusses go perpendicular to the ridge. And the reason for that is that I can build a ridge into a truss like this. I can very easily, it can easily be done. I can't do it, but it can easily be done to build a ridge into a truss. And then we can put the trusses side by side, and that ridge will exist right there. If you were going to try to do it the other way, so that the trusses were parallel to the ridge, you can go through that thought exercise. You'll have to have a truss, and then the next truss over will have to be slightly taller. The next one over will have to be slightly taller than that, and slightly taller than that, and slightly taller than that, and so on. I'm just drawing these kind of side by side, even though that's not exactly how they'd be installed. But you'd have to have trusses. Every truss would be different from the truss next to it. And then you would have roof sheathing, right, being plywood that would go like this. And the trusses would go like this. Let's fix that. You'd have a truss, come on, truss, and then another truss, and then another truss that was slightly taller. And notice how the truss isn't fully in contact with the roof sheathing. That's an awkward connection where the roof sheathing is bearing on the edge of the truss. Okay, so these are the reasons why we just build the ridge right into the trusses like that, and then that means that the truss length, here's the ridge, and the trusses are perpendicular to that ridge. Probably said it enough times now for you to understand it 4 times over. Okay, notice here that this is the exterior wall. See, I want to do about half an hour of talking, so we've got about 5 more minutes left, 6 more. So this is the exterior wall in here, under there, and notice that here is the edge of the roof. The edge of the roof is extending beyond the exterior wall. That is called an eave. The house roof extends beyond the exterior wall, and the reason for that is that when it rains, the roof will shed the rain off either into a gutter, or the water will fall off the roof away from the walls. You won't have water just running down the face of the wall, as would happen if the roof edge ended right at the face of the wall. We don't want water running down the walls because structures are water resistant, they're not watertight. So if we have the opportunity to get water off or to keep it from touching the building at all, that's preferable to having it run down the walls, run like dust and crap down the face of the wall, stain the wall, and then maybe discover some crack, some leak in the wall, and have water go inside the wall and cause mold. So this is why we have eaves. Let's see here. Here is a beam. That's called a header. That beam goes over. It looks like right here there's a door. Whoops, that's not what I want. Okay, so there's a door here, and then as I talked about in a previous lecture, that door should swing open like that. There should be a door swing image like that. It indicates a door, and then the rest of that will be a window next to the door. So doors and windows do not support the roof, therefore we have to put a hardened structural element right there above the door and window. I've called this out as B1 4x12. So what does B1 refer to? If I go into the calculations and I go into, let's see here. There we go. The beam calculation for beam 1. B1 is a reference number. It's showing the plan checker or myself later, hey, this is beam 1. This is that beam that we're talking about. It's that one, that B1. This is actually not a piece of information that's for the contractor. The contractor will just ignore that B1. I should have something in my symbols that tells them basically that. Here, reference beam label for building department use. It means contractor, don't worry about what B1 means. All you need to know is that's a 4 by whatever is indicated on plan. So in this case, it's a 4x12. But if I come to you, and I say, all right, can you show me the calculation for beam 1? You can go into your calcs and you can just skim through them like this, B1, 2, 3, blah, 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 and you know right there that beam 1, okay, we're looking at the same beam. Okay, that's a 4x12, and the moment demand on that is 86%, which is well under 100%, and it's under 95% too, which is good. We don't want beams to be too super duper stressed out, because one reason is sometimes we can accidentally underestimate the load that will be on the beam, and another is that sometimes there's a flaw in the beam that nobody expected to be there. Even though beam grading does exist, it's not a perfect science. It's often done by eye, just by people looking at pieces of wood and deciding what grade they should have. There could be a small crack in a beam that nobody saw. So we don't want to design things up to 99% capacity. Usually 95% or less would be good, or 90%. Here is the scale, okay? This is showing us that on this page, as printed, on a 24-inch by 36-inch sheet, which is the standard size for structural and architectural plans, 1/4 inch measured on that sheet will represent 1 foot of length in the real world. So I can use the Bluebeam software that I use and love. Here, come back. This is 1 and 4, that's 1/4 inch. And I could scale the length of this beam. 9'2". Here, maybe it needs to go a little bit farther there. 9'2½". Now, if I go check my beam calculation, I better find that the beam in my calcs is somewhere right, pretty close to that, and not shorter than it. So there, 9'3". Okay, great. Overestimating the beam length slightly is fine. That will yield a somewhat conservative design. We never want to, like if I saw 9'1" here, I would be bothered by that. So we should not be underestimating beam lengths because that will cause unconservative beam designs. Okay, so that's roof framing plan, foundation plan. I'll finish up with this sheet and then quit the lecture for now, for this lecture. Foundation notes, build per plan. I wouldn't think I would need to say this, but I have actually encountered contractors who actually think that the structural plans are a suggestion. That's not true. That is against the law. That's not how anybody sees it. Architects don't see it that way. Building department officials, engineers, clients, lawyers, judges, Nobody sees it that way, and even most contractors don't see it that way. Only foolish fools of contractors who are just belligerent, disrespectful people, disrespectful to the system, see the structural plans as a suggestion. And so I have written build per plan. The structural plans represent construction practices required by California law. That way, if I come out and find a contractor's ignoring the plan, I'm going to hit him over the head with foundation note number 1 and framing note number 1 too. It's actually on here twice. This second note, for information not shown, refer to general notes and typical details. I've had contractors who said, "Where are the wood grades? How am I supposed to know what beam? What is this, a dug for 1 beam or a dug for 2?" I'd say check out the general notes, dude. It's right in there in the general notes. Contractor shall verify conditions in the field. Okay, so this is in case let's say I engineered this shear wall to be at least 6 foot 6 inches long. Let's say I misunderstood something about the architectural drawings, or the architect changed the length of the wall without telling me, and in fact there's only 5 feet there or 4 feet there. The contractor will be the last person to catch this, probably. Yes, a building department inspector might notice it, but I would hope that a contractor catches this before the thing gets built. And the contractor will know that, will see that problem, verify conditions in the field, and if a discrepancy exists, notify designer or architect and engineer immediately. Like, don't keep building, tell me there's a problem. Okay, sill plate anchor bolts should be at least 5/8 diameter and spaced at 4 feet on center. That means 4 feet apart. UNO. That means unless noted otherwise, and that should be something that's in the abbreviations in the general notes. There it is. UNO stands for unless noted otherwise. I have actually modified that just a little bit to say unless a heavier design is required per plan. Every now and then you'll encounter a case where you specify something on plan and call it UNO, and then you accidentally specify a smaller thing somewhere else on plan and you didn't mean to. And what you really want is that nothing be smaller than the unless noted otherwise design. And it's only, a thing is only more heavy duty than the UNO when you want it to be more heavy duty, but is never less. So by changing UNO to say unless a heavier design is required by plan, then that makes it so nobody should interpret me as specifying some piece of hardware that's below the UNO floor. I know I kind of hit you with a drive-by of this definition of UNO. We can talk about it later, but basically UNO, it just means unless noted otherwise. It means do what I'm saying right here in general, unless I tell you to do something different. Unless noted otherwise, do this. There's an example, 4x6 UNO, unless noted otherwise. So for wood columns, this is me saying, if I were to show you just the image of this square on plan, or rectangle, without a size attached to it, it means 4x6 column, even if I don't indicate anything, because it's 4x6 unless noted otherwise. So if I wanted then a 4x8, I would specify a 4x8 specifically next to the column. There's epoxy. We can talk more about that later. Sill plate anchor bolts, hardware and fasteners in preservative treated sill plates shall be hot dipped galvanized. Preservative treated, the sill plate, remember, is that piece of wood that lies along the foundation and the wall sits on top of it. The studs in the wall sit on top of it. Concrete is porous, so moisture in the soil can wick up through the concrete and get in contact with the sill plate. Wood rots when it is repeatedly put in contact with moisture, so sill plates are often, always, preservative treated unless they're made of redwood, but most often they're preservative treated. Often it's called a green sill. The treatment that is put into them has copper in it, and the copper, I guess, turns green because it's oxidizing. I don't know. So, but you'll see sill plates that are green, and that means they've been preservative treated. And what this note is saying is any hardware or fasteners in preservative treated, or otherwise known as PT sill plates, shall be hot dipped galvanized. The preservative treatment can cause the fasteners to rust. and so we don't want that to happen. So that means any fasteners, steel fasteners that are in the sill plate, we don't want those things rusting, and so they should be hot dip galvanized, which means coating them in a layer of zinc, which is a corrosion resistant metal. Okay, so you can take some time to look through these notes on your own, and if any of them are not clear to you, let me know. We can talk about them. I think that's a good plan of action. Here's a roof sheathing specification. It's saying the roof sheathing shall be a half-inch thick. Half-inch sheathing means half-inch thick. Sheathing rated by the American Plywood Association, APA. 32 on 16 panels. So that means that for roof live loads of 20 PSF, right? Roof live loads there's a lighter load we expect roofs to carry because you don't have parties on the roof. We would expect a panel like this to be able to span over roof rafters that are 32 inches apart and still be able to support the load from that. But because floor loads are heavier, and you can have such a thing as a piano and a floor load, or a party, or an aquarium, we would count on that half-inch thick panel to only be able to extend 16 inches from one joist to the next. And then we can talk about sheathing clips and 2x-flat blocking at unsupported edges later. Nailing shall be per the typical nailing schedule, which is right there. See detail sheet S 3.0. There's a typical nailing schedule. We've looked at this. It just tells for different items that could be nailed together. Top plate to a stud. Here are the nails that should be used to nail those things together. Okay, so I'll cut. Oh, and there's north. We always need to indicate which way is north. So I will cut it for tonight, and thank you very much for listening.